allows the entrance of certain molecules, ions, whatever, into the cell. They don't necessarily then have to pass through the phospholipids or between the phospholipids. They've got a channel by which they can go through. So when I say a gate, like an example would be a gate in a picket fence, that gate can be opened, it can be shut, and it can be locked. So this is fairly common with these kinds of channels. The channels are often very specific to a particular entity that needs to get in or out. Many of the channels emit ions. And an ion is a charged particle, such as hydrogen ions, calcium ions, potassium ions, and a variety of others. Sodium, chlorine, and so on. So we refer to them as a calcium channel, or a sodium channel, or a potassium channel, because they are indeed very specific. So here we have a channel that has an opening that's going to admit or allow to exit a certain ion or small groups of proteins like polypeptides. Not very big proteins because they wouldn't fit. Now, here we have our mouth of the channel. And the first problem that we encounter is how the heck does something get into that channel? What kind of forces are at play that allow this to happen? Well, first of all, you might remember that what I said about miniaturizing yourself, crawling inside your cell, and encountering all of these molecules that are whizzing by at great speed. One of the things that causes that great speed is a concept that you were introduced to in basic biology called diffusion. And remember, particles that start off in a high concentration move from high concentration to a low concentration. How do they do that? What causes them actually to kind of move away from that area of high concentration?
Hypotonic and hypertonic.
That's more with osmosis, but there's movement there as well, certainly. Okay, imagine a cluster, a close cluster of individual things. They have their own movement, particularly in your body, where they have a movement that's reflected of your body temperature. So they move about and they collide with one another. And indeed, it's these random collisions that is going to separate them. If I put another 50 students in this classroom, I remove the tables and put you all in chairs with wheels on them. And I cranked up the temperature so that you started off shoulder to shoulder. Pretty much you'd be so hot that you'd be bumping the student next to you. And so over a period of time, there'd be a greater distance between you and your neighbor. And it's these random collisions that set these molecules, these ions, into motion. So we can imagine then that there's a lot of motion in the interstitial fluid. So this is the outside, or the ECF, and this is going to be the ICF, on the inside of the cell. So lots of things going on, lots of collisions that are going to eventually push things towards the mouth of the channel. Now, you might imagine then that we've got, let's say, sodium in fairly high concentration. It can be any ion, it doesn't matter either. And now they're sort of in the neighborhood of the channel, but not really entering it. But would this help? could put negative charges around the mouth. Yeah, I think you could bet some cold hard cash that at least you get some sodium molecules entering the channel. And remember, they have their own movement. And so consequently, when they're in the neighborhood, they tend to be sort of sucked in, if you will, into the channel. Yes?
So are the channels always negative?
No,
Okay.
no. And that, again, it would depend on the nature of the ion or the molecule. So I'm just supposing here that they do have a charge. Items that don't have a charge are going to have to get into the cell or out of the cell by different mechanisms. All right. So now we've got some sort of attractive force in addition to the molecular or ion movement above that, and that movement is severe. Then you could sort of propose that you would have alternating charges all the way down the interior of this protein channel. Now remember, proteins are made up of amino acids, so there's charges there that are involved. And so if you look at it, it is sort of a push-pull kind of motion from the entrance to the exit. So that as the molecule comes in, it's plus, that's going to push it in this way because it's attracted by the negative and keep it moving through the channel. Now remember, these channels can be locked tight so that there's no movement of molecules, that there's no possibility of sodium to enter it. And again, they can be locked as well. So it takes some energy to open them up. But this is the nature of a channel. And again, they tend to be very, very specific. All right with this? So here's another way in which molecules might be able to enter plasma membrane or cell. And that indeed is the idea of an enzyme that is actually mounted at the surface. So here's our membrane-bound enzyme. And here we have something that is not going to be able to enter because of its size. And so consequently, when the enzyme grabs it in this way and then eventually breaks it down,